Mars hangs like an ember against the void, and every instrument watching it blinks the same warning at once. 2:17 UTC, the 9th of October 2025, telemetry stutters, then locks. A star-silent object skims past the planet's orbit and does something it should not. No luminous tail, no dusty shroud, just a pinpoint that drifts, hesitates, and sidesteps by a whisper thinner than breath. On board Mars Express, the attitude wheels hum. A guidance log notes a fractional arc-second shift. ExoMars follows a minute later, 2:18 UTC, confirming the nudge as if an invisible hand pressed against the traveler's flank. Across Earth's night side, coffee goes cold beside keyboards. Screens fill with residual plots and residual doubts. Someone reruns the fit. The curve won't sit still. Another analyst toggles the non-gravitational parameter and watches the model relax, almost relieved, almost alarmed. A spectrometer team drops a message into the cascade. Weak emissions suggest stray. Oh, a ghost of water where the sun's heat can't yet lay its claim beyond 3 AU, beyond reason as we tidy it. Mars rolls on, indifferent. The object doesn't flare, doesn't announce itself, only trims its path beside the red planet, as neatly as a scalpel tracing skin. At 2:23 UTC, the feeds settle, and the room full of people who keep space honest realize they're suddenly part of a story that wasn't in the script. Gravity explains so much until it doesn't. And on this cold October morning, next to Mars, the sky chooses to keep one secret less and one mystery more. Tonight, we embark on a new journey, where the theme of 3I Atlas just altered course, next to Mars, and it changes. Everything appears not only as a scientific phenomenon, but also as a question that challenges our imagination. If you enjoy this kind of quiet, long-form storytelling, if it helps you learn, focus, or simply relax at the end of a noisy day, take a moment to like the video and subscribe, but only if this space truly brings you peace. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. The mystery deepens. What if the change wasn't an illusion at all? What if, in that faint adjustment beside Mars, we are witnessing an interstellar object responding to a force not yet written in our equations? The trajectory of the interstellar object designated 3I Atlas presents a celestial puzzle, one that challenges the very frameworks through which we interpret motion through the void. As it performed its gravitational swing past Mars in the observational window of late 2025, a subtle anomaly was recorded. According to current models of celestial mechanics, its path should have been dictated solely by the gravitational pull of the Sun, with Mars providing a minor, perfectly calculable perturbation. The initial data, a tapestry woven from the continuous observations of orbiters like the Mars Express, operational since December 2003, and the Mars Reconnaissance Orbiter, with its high-resolution camera watching since March 2006, seemed to confirm this predictable dance. The object's velocity, its angle of approach, all fell within expected parameters, a testament to the power of Newtonian and Einsteinian physics. Yet, in the precise moments of its closest approach, a discrepancy emerged, a whisper of a deviation that the most sophisticated orbital filters could not entirely erase. Could this be mere statistical noise, an artifact of combining datasets from different epochs and different instruments? Or are we witnessing the first faint signature of something beyond our current comprehension? The mainstream explanation points towards the complex environment of Mars itself. The European Space Agency's ExoMars Trace Gas Orbiter, conducting its regular science since 2018, has meticulously mapped the Martian exosphere, a tenuous envelope of gases. Spectral analyses have long indicated the presence of hydroxyl, a key signature of water vapor dissociation, even when the planet is far from the Sunday. It is scientifically plausible that, as 3I Atlas, a body likely rich in volatile ices, ventured through this region, a localized and transient outgassing event occurred. Solar heating, perhaps amplified by some unique surface property of the object, could have triggered a jet of water vapor at just the right moment and orientation. This would impart a minute non-gravitational force, a gentle nudge that would appear to us as a slight course correction. Such phenomena are not unheard of. Comets within our own system exhibit non-gravitational accelerations due to outgassing. But does this conventional mechanism fully account for the specific timing and the vector of the observed trajectory shift, a change that seemed to optimize its exit path from the inner solar system? This leads to a more speculative hypothesis. Imagine if the object did not merely encounter a random pocket of the Martian exosphere, but instead interacted with it in a purposeful manner. What if the magnetic field of Mars, a relic of a dynamo long dormant, acted not as a passive barrier, but as a trigger? One could envision 3I Atlas possessing a latent, complex chemistry on its surface, a chemistry sensitive to specific electromagnetic conditions. As it crossed the boundary of the Martian magnetosphere, this interaction could have activated a preordained mechanism, a switch of ancient and inscrutable design, initiating a controlled venting of volatiles. This would be less like a random geyser and more like the firing of a thruster. Another analogy lies in the innate, genetically encoded navigation of migratory birds on Earth, which use the planet's magnetic field as a guide. Could this object possess a form of cosmic instinct, a built-in propensity to use planetary encounters for course refinement? Is it conceivable that we are not looking at a rock, but at a vessel equipped with a form of natural propulsion, a self-steering mechanism that subtly alters its solar system escape vector? The implications of such a possibility are profound, reshaping the future of interstellar exploration. If the course correction is verified as a real non-gravitational event, and if its source is indeed the sublimation and directed ejection of water ice, then we are witnessing a demonstration of a technology, either natural or artificial, of immense utility. Humanity's ventures beyond the heliosphere are currently limited by the tyranny of propellant mass and the long durations of travel. A steam sail concept could emerge, where a spacecraft harnesses the very ices it carries as both a shield and a propellant reserve. By carefully timing the heating and venting of these ices during planetary flybys, a craft could perform delicate trajectory adjustments without the need for complex, heavy chemical engines. It would turn a passive celestial object into an active navigator of the galaxy. But can we ever distinguish between a naturally occurring outgassing jet and a deliberate maneuver? The answer may lie in the precise data collected in the moments following its Martian encounter. For now, the International Orbital Calculation Centers are refining their models, incorporating every byte of telemetry from our Martian sentinels. They have noted a small but persistent discrepancy in the path of 3I Atlas. A change of merely a few thousandths of an astronomical unit may seem infinitesimal on the scale of the solar system, yet over light years, such a deviation compounds into a vast angular shift, potentially altering its ultimate destination among the stars. Was this a random event or a calculated adjustment? The object continues on its journey, carrying its secrets with it into the darkness, leaving us to ponder the nature of its guidance. And as it departs, a new question arises from the latest orbital solutions, a question that hinges on the most minute of measurements. Will the updated trajectory following the Mars flyby reveal a sudden, definitive jump in its non-gravitational parameters? Following the Mars gravity assist in late 2025, the orbital solution for the interstellar object 3I Atlas was updated with a startling revelation. The non-gravitational parameters, which had previously hovered statistically near zero, exhibited a sharp, discontinuous jump to a finite, measurable value. From the perspective of conventional celestial mechanics, this presents a classic puzzle of signal versus noise. Was this a mere statistical artifact, a phantom in the data processing, or was it a genuine physical impulse, a nudge imparted to the object as it swept past the red planet? The trajectory fit post-flyby now demands two distinct dynamical models, a 1 for the approach and a 2 for the departure, a bifurcation in its kinematic history. Even a deviation of a few thousandths of an astronomical unit, seemingly insignificant in the moment, can accumulate into a vast positional error over the object's hyperbolic trajectory into the depths of interstellar space. Could such a minute, unaccounted-for force be the key to understanding its true nature? The immediate, mainstream interpretation points towards more prosaic, albeit fascinating, explanations. One hypothesis suggests this kinematic break is not a physical event at all, but rather an artifact of updating the planetary ephemeris. The precise positions of Mars and its moons at the moment of the flyby are known only to a certain accuracy. A slight refinement in this foundational data could manifest as a sudden shift in the calculated forces acting on 3I Atlas. Alternatively, scientists might posit a short, intense burst of outgassing, a single, sealed vent rupturing under tidal stresses, or a pocket of super-volatile ices sublimating in the Martian proximity, could provide the necessary jet-like thrust. This would be a transient, localized activity, a brief sputter from an object otherwise in a deep cryogenic sleep. Yet, does a single burst fully account for the sustained change in the non-gravitational parameters, or does it merely mask a deeper, more persistent transition? A more speculative line of inquiry ventures into the realm of material science and electromagnetism. Could 3I Atlas carry a latent, accumulated thermal mechanical scar from its eons-long journey between the stars? This structural weakness, a fault line in its cryptic architecture, might have been triggered by the specific frequency and intensity of Martian radiation, a resonant key unlocking a dormant mechanism. Or perhaps, the tenuous but electrically active dust envelope of Mars provided the catalyst. A single micron-sized charged dust grain, impacting at hypervelocity, could theoretically induce a localized Lorentz force, a microscopic push on a charged surface patch, a force negligible for a spacecraft but potentially significant for a small, low-mass interstellar traveler. Is it possible we are witnessing not simple outgassing, but the activation of a complex, integrated system responding to its environment? Our capacity to discern between these possibilities rests upon the shoulders of our robotic sentinels at Mars. The Mars Express, operational since its orbit insertion in December 2003, the Mars Reconnaissance Orbiter, with its high-resolution cameras since March 2006, and the ExoMars Trace Gas Orbiter, a dedicated atmospheric chemist since its science phase began in 2018, all turned their instruments towards the fleeting visitor. Their collective data visual, spectroscopic, and positional forms the bedrock of this investigation. They are the independent witnesses to the event, their silent observations filtering back to Earth, providing the crucial context for the telemetry. But can even this formidable network capture every subtle interaction, every whisper of force exchanged between a world and a wanderer? The implications of this anomaly are profound, rippling through the foundations of astrodynamics and interstellar object studies. On one hand, it presents a serendipitous calibration opportunity, a controlled, measurable change in the non-gravitational forces triggered by a known event allows scientists to refine their models of outgassing torques and radiation pressures with unprecedented precision. It is a natural experiment conducted on a galactic scale. On the other hand, it introduces a significant risk to long-term forecasting. If the forces are not transient but represent a new, active phase for the object, our ability to predict its future path through the galaxy becomes unstable, its trajectory now subject to the whims of its own hidden internal dynamics. Have we, in our attempt to chart its course, inadvertently discovered that the map is alive and changing? This sudden activation, This brief flare of non-gravitational motion as it passed Mars forces us to reconsider the very activity of the object itself. The initial analysis from the flyby data suggests an object stirring, perhaps awakening, and this leads our inquiry to a prior, equally puzzling observation, one made while 3I Atlas was still far from the inner solar system. Spectral observations from the James Webb Space Telescope had already detected the faint but unmistakable signatures of water vapor and hydroxyl radicals at a heliocentric distance of nearly 3 astronomical units, a region far too cold for traditional sublimation of water ice. It displayed a coma without a visible tail, a halo of activity without the directional jet of a sun-driven comet. What internal energy source, what exotic mechanism of material release could possibly explain this anomalous activity in the deep freeze of the outer solar system? The initial observations presented a profound anomaly, a celestial body drifting near 3 astronomical units from the Sun, a distance where the warmth of our star is, but a faint memory and cometary activity is expected to be dormant. Yet, the data revealed a faint but distinct coma, a tenuous shroud of gas and dust enveloping the object. There was no magnificent tail streaming away, no classic signature of a sun-warmed ice vaporizing under solar radiation. Instead, this was a localized, almost intimate halo of activity. It suggested not a surface-wide eruption, but a focused, almost deliberate process. Could this be the signature of a hidden engine, a mechanism working silently in the deep cold, far beyond the expected boundaries of cometary awakening? Mainstream science would first turn to the well-established process of sublimation. Perhaps this object possesses a reservoir of hypervolatile ices, such as carbon monoxide, whose freezing point is so low that even the meager energy at 3 AU could trigger a phase change from solid directly to gas. The energy for this process might not come from the distant sun alone, but could be supplemented by the relentless bombardment of cosmic rays, penetrating the surface and providing the necessary joules to liberate these super ices. This would create a low-level persistent outgassing, just sufficient to lift the finest dust grains and form a faint coma. But does the gentle nudge of cosmic rays truly possess the power to sculpt such a defined and sustained exhalation, or are we witnessing a far more targeted release? The spectral evidence, however, anchors this mystery in tangible reality. The detection of the hydroxyl radical, a well-known product of the photodissociation of water molecules in the near-ultraviolet range around 3085 angstroms, is a definitive signature. This is a wavelength historically documented in cometary Camus, much closer to the Sun, where liquid water is impossible but water ice sublimates readily. Its presence here, at 3 AU, is deeply confounding. It implies that water molecules are being broken apart by solar photons, which in turn demands that water vapor is present. How can water ice sublimate in the profound cold of the outer asteroid belt, where temperatures are perpetually locked far below the point where water ice should remain inert? What unique physical chemistry could be at work on this object's surface? One hypothesis ventures into the realm of electrostatic phenomena. The ultrafine dust observed within the coma may not be lifted by gas flow alone. In the vacuum of space, exposed to solar ultraviolet radiation and plasma, surface grains can acquire significant electrostatic charges. This static levitation could allow the smallest particles to rise and form a dust halo, even with minimal gas production, creating the illusion of a more active body. Yet, this does not explain the source of the water vapor itself. Is the dust merely a passive passenger, or is its movement a clue to a more complex system of forces at play beneath the surface? A more speculative proposal involves a temporary and selective valve mechanism. Imagine a composite ice, a clathrate structure where volatile gases like carbon monoxide are trapped within cages of water ice. As cosmic rays or residual heat destabilize this matrix, The building pressure of the sublimating superices could force open microscopic pathways, creating a transient, focused jet. This would not be a uniform outgassing, but a highly directional vent, a temporary opening in a network of subsurface capillaries. The coma, then, would not be a uniform shell, but the product of a concentrated, if fleeting, geyser. Does this object possess a complex, engineered-looking internal plumbing system, concentrating its limited energy into precise, directional thrusts? The implications of such a mechanism are staggering. It forces a complete redefinition of what we consider the active zone for comets. If objects can maintain a form of polar, metabolic function in the deep freeze beyond 3 AU, our census of active bodies in our solar system is profoundly incomplete. This remote, cold region of our system could be dotted with such dormant engines, only occasionally flickering to life. It transforms this vast space from an empty frontier into a potential network of way stations, of naturally occurring fuel depots rich with water ice, waiting for a future era of interplanetary travel. But is this a natural resource, or was it placed there for a purpose we cannot yet fathom? This leads us to the next, even more perplexing characteristic of this visitor, its unwavering trajectory. If this activity were driven by significant outgassing, one would expect a measurable non-gravitational acceleration, a jet effect, subtly altering its path around the Sunday. The absence of such a deviation presents a formidable puzzle. If there is no significant rocket-like thrust, then the object's mass must be far greater than any known comet to resist the cumulative effect of even small jets. Could it be that we are not looking at a fragile aggregate of ice and dust, but at something far denser, a fossilized cometary core of immense proportions, whose faint coma is but a whisper from a monolithic, ancient structure? The initial data stream from the tracking arrays presented a quiet enigma. For an object designated as a comet, 3I Atlas displayed a profound and unsettling stillness. According to current models, a comet approaching the inner solar system should awaken under the solar wind, its volatile ices sublimating into a tenuous atmosphere that streams away to form a luminous coma. This very process of outgassing typically imparts a slight but measurable non-gravitational acceleration, a gentle jet-propelled nudge that subtly alters the object's trajectory from a purely Keplerian path. Yet, the astrometric data for 3I Atlas, painstakingly gathered over weeks of observation, revealed no such deviation. Its motion was governed solely by the immutable pull of gravity, a silent body moving through a silent sea. The instruments, capable of detecting the faintest whisper of a thrust, registered nothing but the cold equations of orbital mechanics. This absence was not merely a lack of data, it was a positive signal of something profoundly unusual. If there is no significant outgassing, no detectable non-gravitational acceleration, then what force, or what fundamental property, holds such perfect dominion over its motion? The most immediate and conservative explanation points to mass. Scientists suggest this could be due to an object of such substantial bulk that any small outgassing jets, which would visibly perturb a typical comet, are rendered negligible. The recoil force is simply swallowed whole by the object's immense inertia. This interpretation finds support in the photometric data, which indicated an unusually low albedo and a steady, unfluctuating brightness. The object was dark, incredibly dark, and its light curve suggested a large monolithic surface, not the fragile, rotating aggregate of a standard cometary nucleus. When compared to our previous interstellar visitors, the difference is stark. Oumuamua, discovered on the 19th of October, 2017, was a small tumbling object whose anomalous acceleration, while debated, was at least detectable. Borisov, discovered on the 30th of August, 2019, behaved as a textbook comet, erupting in a brilliant display of outgassing as it rounded the Sunday. 3I Atlas presents the opposite case, a body that should be active yet slumbers. Could its apparent stillness be not a sign of dormancy, but a testament to a gravitational grip so strong it muffles the very forces that animate its kin? But that does not account for the spectral whispers hidden within that pervasive darkness. Low-resolution spectroscopy had tentatively identified the absorption bands of water ice on its surface. This presents a fundamental paradox. We see the fuel, but we do not witness the engine's fire. How can a body possessing volatile ices so close to the Sun resist the energizing touch of stellar radiation? This contradiction forces us to consider a more speculative hypothesis. Perhaps we are not looking at a conventional comet at all, but a fossilized relic. Imagine a celestial body with a stratified core, a dense, mineralogical heart forged in the furnace of an alien star system. This superdense core could be encased in a thick, durable crust, a shell of carbonaceous material, or complex organics, acting as a formidable insulator. Trapped beneath this armored carapace lie the volatile ices, a cryogenic ocean or a permafrost layer imprisoned by its own geological tomb. The outgassing, if it occurs at all, is not a surface phenomenon but a subsurface process, the pressure building internally with no avenue for escape, its potential thrust cancelled by the sheer structural integrity of the object. Is 3I Atlas not a comet, but a planetary cinder, a drifting crypt for its own volatile soul? This leads to a cascade of analytical inferences. First, the object must be just heavy enough, its mass calibrated to a precise threshold where the minuscule recoil from any feeble, filtered outgassing is reduced below our current detection capabilities. It is a body that exists in a state of perfect gravitational balance, its inertia masking its internal composition. Second, its structure must be profoundly layered, a testament to a complex formation history, far from our own solar system. The dark, durable exterior we observe is merely the outermost layer of an onion-like architecture, each stratum hiding the secrets of the one below. And third, this suggests the existence of an entire class of super-heavy interstellar objects, dark and silent wanderers that have so far evaded our surveys precisely because they do not announce their presence with the brilliant pyrotechnics of a comet. They are the ghosts in the cosmic graveyard, visible only by the light they obscure. What other fundamental properties must such an object possess to maintain its structural cohesion over eons of interstellar travel? The implications of this possibility are as profound as they are practical. If such objects are not rare anomalies but common constituents of the galactic inventory, they represent more than just scientific curiosities. They could become the natural inertial anchors for future missions. A spacecraft could rendezvous with one of these dark wanderers, using its substantial mass for a gravitational assist or even tethering to it, employing its momentum as a slingshot to reach velocities unattainable by conventional propulsion alone. They would be the stepping stones across the interstellar ocean, providing a stable platform for refueling or a shield against cosmic radiation. The very property that makes them so enigmatic, their immense silent mass, could be the key that unlocks the stars for humanity. But to harness such a power, we must first answer a more immediate and unsettling question. If the outgassing is truly absent, what other, more exotic mechanism could be controlling its path? And what does the faint specific signal of hydroxyl at 3085 angstroms reveal about the hidden dynamics stirring beneath that dark, silent crust? For even within the profound stillness, a subtle clue emerged, not in the object's motion, but in its light. Deep within the ultraviolet spectrum, a signature was detected by the most sensitive instruments, the faint but unmistakable emission line of the hydroxyl molecule at 3085 angstroms. This was not the broad, diffuse signal of a general coma, but a sharper, more localized reading. According to current models, the presence of hydroxyl is a direct proxy for water, as water ice is broken apart by solar ultraviolet radiation into hydrogen and hydroxyl. The conventional explanation would be a faint, perhaps asymmetric, outgassing of water vapor from a localized vent on the surface. This would be consistent with the object's overall lack of significant acceleration. The directed jet could explain the presence of the spectral line without providing a global thrust large enough to be measured astrometrically. It would be a whisper of activity where we expected only silence, a small geological sigh from an otherwise inert world, but that does not account for the precise orbital context in which this signal was found. The detection of hydroxyl coincided with the object's passage through the inner solar system, specifically within the gravitational sphere of influence of Mars. And here, the astrometric data, while showing no large-scale non-gravitational acceleration, did reveal a minuscule, persistent anomaly in its trajectory, a slight bending of its path that could not be fully attributed to the gravitational pull of the Sun or the planets. It was as if an invisible hand was giving it the gentlest of pushes. Scientists suggest this could be due to a highly focused, directional jet of gas, a natural thruster operating on a scale we can barely perceive. The recoil from such a phenomenon, if channeled through a narrow nozzle-like geological feature, could indeed impart a small but continuous force. The hydroxyl emission, therefore, might not be a sign of general sublimation, but the exhaust plume of a precise, naturally occurring propulsion system. Could the faint ultraviolet glow be the visible signature of a cosmic engine, firing with a delicacy that belies its power? This introduces a far more speculative hypothesis. What if the water ice is not merely sublimating from a surface vent, but is being actively managed? Imagine a scenario where the object's thick, insulating crust traps a subsurface reservoir of water under pressure. At a specific point in its orbit, perhaps as internal tidal forces from the Sun or Mars reach a critical threshold, a fissure temporarily opens, a tap is turned on. A directed stream of water, vapor, and other volatiles escapes, not as a chaotic geyser, but as a controlled burst. The mechanism for this could be purely geological, a cryovolcanic process where the warming of a specific volatile layer builds pressure until it finds release through a pre-existing weakness in the crust. The resulting jet, the hydroxyl exhaust, provides a slight but steady thrust. This would not be the random outgassing of a typical comet, but a repeatable, directional phenomenon, one capable of making fine adjustments to the object's course over astronomical timescales. Is the trajectory of 3I Atlas not just a product of gravity, but a path that has been subtly guided, a course corrected by its own internal geological logic? The analysis of this possibility leads to a startling inference. The force required to produce the observed orbital deflection within the Martian region is minute, yet over thousands or millions of years, such a force is more than sufficient to radically alter an object's journey through the galaxy. A tiny, continuous nudge can steer a ship across an ocean, given enough time. This implies that such a tap-turning mechanism could be a form of passive navigation. An object equipped with this natural technology could, in theory, use the gentle gravitational tides of stars and planets it passes to trigger its course correction jets. Using the galaxy's own gravity wells as a source of navigational timing, it would be the ultimate expression of slow, patient travel. The presence of hydroxyl at 3085 angstroms, then, is not just a chemical signature. It is the operational log of this process, a readout of the engine's most recent firing. What other spectral lines might we find, if we look closely enough, that would reveal the full complexity of this self-correcting trajectory? The ramifications extend beyond mere celestial mechanics. If this speculative hypothesis holds any weight, it forces us to reconsider the very nature of interstellar objects. They may not be simple, passive lumps of rock and ice, but complex geological systems with their own internal dynamics and long-term evolutionary behaviors. The deflection of its path near Mars would not be a random anomaly, but a predictable outcome of its internal structure, interacting with the solar environment. This transforms such objects from being merely the debris of planetary formation into potential agents with a degree of environmental interaction. They are not just falling through space, they are, in a very real and physical sense, navigating it. The search for life in the universe has often focused on biosignatures, but perhaps we should also be searching for such technosignatures of natural, non-biological engineering evidence of processes that allow simple physical systems to achieve complex, long-term goals. Does the faint ultraviolet glow of hydroxyl represent the first evidence of a naturally occurring propulsion system? And if so, what does that imply about the prevalence and potential destinations of the countless other, silent, dark wanderers that must be drifting between the stars? The faint, ethereal glow of the hydroxyl radical at 3085 angstroms has long been catalogued as a mere spectral footnote in the ultraviolet observations of cometary Comets. A product of water-ice photodissociation, its presence is a direct, if subtle, indicator of the sublimation of water, the very lifeblood of a comet's activity. According to current models, this emission is a passive beacon, a ghostly signature of a process that occurs millions of kilometers from the warming touch of the Sunday. It is the final, ultraviolet whisper of a water molecule shattered by solar photons, a predictable and measured phenomenon. Yet, what if this whisper is not a passive sigh, but an active command? The detection of this specific line in the context of an interstellar object like 3I Borisov, or the anticipated observations of future visitors, presents an anomaly that challenges our passive interpretation. The precise wavelength, 3085 angstroms, coincides not just with a chemical process, but potentially with a mechanical one, a resonant frequency that could act upon the comet's own structure. Could this ultraviolet photon be the audible click of a cosmic tap being turned on, its energy not merely a byproduct of destruction, but the trigger for a release? If water sublimation is the comet's breath, then is the OH line the precise moment an exhale is directed, a jet is born? The mainstream explanation for non-gravitational accelerations in comets relies on the asymmetric outgassing of volatiles. Heated primarily on the sunward side, ice is turned to gas that streams off the nucleus, creating a weak but persistent thrust that can subtly alter an orbit over time. This is a well-established principle, supported by decades of astrometric data from countless comets within our own solar system. The jets and fans observed in cometary Comets are the visible manifestations of this process, and the OH radical is simply one of the many chemical traces we use to map this activity. However, that model presupposes a relatively homogeneous, if patchy, surface. It does not adequately account for the potential of a subsurface, pressurized system. Imagine not a slow, steady sublimation from a surface layer, but a vast, subterranean aquifer of water ice, sealed beneath a non-volatile crust. As solar heat slowly conducts through this crust, the ice beneath does not just sublime, it turns to vapor, building pressure in confined chambers. The OH emission at 3085 angstroms could then be the spectral signature of a pressure release valve, a geyser-like jet erupting through a fissure in the crust. The photon is emitted the instant the pressurized water vapor is exposed to the play, the vacuum of space, and the full fury of solar ultraviolet radiation. The click of the tap is the rupture of the seal. But what geological forces could create such a precise plumbing system on a body that has drifted between stars for eons? This speculative hypothesis of a burst and spill mechanism gains further intrigue when we consider the interaction with the solar wind. The newly liberated water vapor, now a jet, is not neutral. It is a plasma, rich in ions and radicals. As this charged plume expands, it would interact with the magnetized, supersonic flow of the solar wind. The resulting friction, a complex dance of electromagnetic forces, could act as a rudder on the jet itself. The solar wind, a constant stream from the sun, could pinch and shape the outflow, potentially aligning it or deflecting it in a consistent direction. This is no longer a simple rocket effect. It is a magneto-hydrodynamic steering mechanism. The jet provides the thrust, but the solar wind may help to aim it. Could the seemingly random direction of a cometary jet be, in fact, guided by the invisible hand of the heliospheric current sheet? Precedent for this exists, albeit in a more muted form, in the historical records of our solar system's comets. Ground-based and spaceborne observatories have occasionally detected faint transient enhancements in near-UV-OH emissions from certain comets, events that were sometimes followed by measurable perturbations in their orbits. These were often dismissed as statistical noise or the result of a particularly large chunk of the nucleus disintegrating. But if we re-examine these old datasets with this new hypothesis in mind, a pattern may emerge. The planned ultraviolet observations of interstellar objects in the coming years, particularly during the windows of their closest approach, are not merely exercises in spectral classification, they are a direct test. If a sharp, localized spike in the 3085 angstrom line is observed, and if that event is followed hours or days later by a detectable astrometric shift in the object's trajectory, the correlation would be profound. The comet would have, in effect, written its own course correction in the language of ultraviolet light. Are we, then, on the verge of learning to read the steering commands of celestial wanderers? The implications of such a mechanism are vast, transforming our understanding of cometary dynamics. A short, powerful jet, triggered by such a release, would impart a small but instantaneous change in velocity. It would be a gentle nudge, a minor correction. But if these jets occur in a rotating body, firing not randomly but in an alternating, coordinated sequence, the effect could be cumulative. A series of such nudges, carefully timed with the object's rotation, could act like a microscopic propulsion system, steadily adding a vector of acceleration in a preferred direction over weeks or months. This is no longer a simple outgassing force. It is a form of crude, natural thrust vectoring. Furthermore, consider a jet that is not brief, but enduring. A fissure remains open, and a steady, pressurized flow of vapor and entrained dust particles continues for days. If this jet contains a significant fraction of heavier, dust-sized ice grains, the momentum transfer is vastly greater. Water vapor is light. A microscopic grain of water ice is millions of times more massive. The expulsion of such material would be a far more efficient propellant. A persistent jet of this nature, acting as a lever arm on the rotating nucleus, could create a sustained torque. It would not just push the comet, it could pivot it, creating a hinge in its orbital path, a subtle but real change in its celestial arc. Is the trajectory of an interstellar object not just a path through gravity wells, but a scribble drawn by the intermittent firing of its own internal engines? The practical consequence is that the hydroxyl radical at 3085 angstroms becomes more than a chemical tracer. It becomes a natural jet clock. By monitoring this specific ultraviolet signature, we could, in theory, predict periods of heightened non-gravitational acceleration. This would allow us to optimize our entire observational campaign. Ground-based infrared telescopes could be tasked to stare at the precise moments following a predicted UV flare, searching for the thermal signature of warm, freshly exposed ice or dust in the jet. We would no longer be passive observers of cometary activity, we would be anticipating its maneuvers. The faint glow in the ultraviolet becomes the second hand on the clockwork of cometary propulsion. But if we can hear the clock tick, can we then predict the direction of its next move? This line of inquiry naturally leads us from the initial trigger of the jet to the very substance it carries. The short, sharp burst of OH emission signals the opening of the valve, but what flows through the pipe? The jet is not pure gas. It is a turbulent mix of vapor and solid debris, a torrent of primordial material excavated from the depths. While the vapor quickly disperses, the larger, dust-sized ice grains possess greater momentum and persistence. They do not vanish instantly into the vacuum. Instead, they travel with the jet, forming a coherent stream that can persist for thousands of kilometers within the coma. This is not the fine, isotropic dust that forms the classic dust tail, pushed radially away from the sun by radiation pressure. This is something different, a concentrated river of material flowing from a specific point on the nucleus. Could these larger, more resilient ice grains within the coma be the source of a sustained push, one that creates the elusive anti-tail? The mainstream explanation for an anti-tail, a spike of dust pointing toward the sun, is a perspective effect. It is often described as the thicker, larger dust grains lagging behind the comet in its orbit, forming a disk in the orbital plane, which from certain viewing angles appears to project sunward. This is a geometric illusion, a trick of light and orbital mechanics, and it requires no continuous force beyond the initial ejection and solar gravity. However, that purely geometric model may be incomplete. What if the anti-tail is not merely an illusion of perspective, but a real, active structure? A durable and prolific jet, rich in these larger ice grains, could act as a continuous, low-thrust engine. The grains, once ejected, would not simply follow ballistic trajectories. If they continue to sublime slowly, their own outgassing would provide a minute but persistent acceleration. This is not the violent burst of the initial jet, but a slow, steady burn. A stream of such grains, emanating constantly from a fixed jet, would form a persistent plume. This plume, viewed edge-on from Earth, would indeed appear as a linear feature, but its alignment and persistence could be actively maintained by the ongoing, microscopic thrust from each sublimating grain within the stream. The anti-tail would then be less a fossil trail and more a living, dynamic engine exhaust. Is what we perceive as a static spike of dust actually a river of microscopic thrusters, each contributing to a collective force? The data from past comets occasionally shows anti-tails that exhibit subtle changes in brightness and orientation that are difficult to explain by geometry alone. These variations could be the signature of changes in the grain flow from the nucleus jet. A steady stream would maintain the anti-tail, a surge in activity would intensify it, a cessation would cause it to dissipate. This directly links the surface activity, signaled by the OH flash, to a large-scale, persistent structure in the coma. The jet is the birthplace, and the anti-tail is its enduring influence, its long-reaching arm. The cumulative effect of this process cannot be overstated. A single jet-altering velocity is one thing, but a durable stream of heavy ice grains, providing a small but continuous thrust over months, represents a different class of propulsion entirely. It is the difference between a firecracker and a slow-burning fuse. This micro-acceleration, negligible on human timescales, becomes significant over the vast distances of an orbit. It could gently shepherd the comet onto a new path, a deviation that would be imperceptible week to week but profound over a year. The force is tiny, but its duration is astronomical. Could such a mechanism be the missing piece in explaining the long-term orbital evolution of some comets, a gentle, persistent nudge that guides them over millennia? This concept forces us to reconsider the very nature of a comet's interaction with its environment. We must ask if the coma is not just a halo of debris, but an extended propulsion system. Each large ice grain, sublimating in sunlight, is a tiny rocket motor. A jet filled with billions of such grains becomes a distributed engine, its thrust integrated across a vast volume of space. The anti-tail, then, is the visible manifestation of this engine's exhaust plume. It is a structure that both reveals and contributes to the comet's journey. And if this is true for comets within our solar system, what sophisticated propulsion systems might be encoded in the light of those that have arrived from between the stars? The detection of the OH line is the first clue, the sound of the engine starting. But the anti-tail is its long, slow, burning testimony. What other secrets are written in the dust, if only we learn to read the language of their persistent, thrusting glow? In the deep exposures of 2025, the faint glow of Comet 3I Atlas reveals a structure that defies simple classification. Beyond the expected dust and ion tails, a faint, sharp spike points directly toward the Sun, an anomaly known as an anti-tail. This feature, a needle of light in the cosmic haystack, is not a tail in the conventional sense, but a geometric illusion, a line of sight through a sheet of large particles trailing the comet's orbit. The conventional explanation posits that this is merely a population of millimeter-sized dust and ice grains, too substantial to be swept back by solar radiation pressure, thus remaining in the comet's orbital path. They are the laggards, the slow-moving debris that paints a line of sight directly back along the comet's wake. Yet, the persistence and stability of this anti-tail in 3I Atlas are peculiar. It does not waver or dissipate, as one would expect from a simple cloud of gravel. It maintains a precise, unwavering orientation, a needle that consistently points back at the Sun with an almost deliberate steadiness. Could this be merely a trick of perspective, or does it hint at a more structured, more substantial population of matter within the coma? The historical precedent for such a phenomenon offers both context and deepening mystery. The comet Arend-Roland, in April 1957, presented a spectacular anti-tail that captivated astronomers. The prevailing model interprets this as a similar sheet of large particles, a testament to the range of grain sizes a comet can eject. Scientists suggest this could be due to the fragmentation of a particularly dense and icy crust on the comet's nucleus, releasing a wave of robust fragments that resist the Sun's push. According to current models of cometary outgassing, the force of sublimating ices like water and carbon dioxide can carry along a distribution of dust, with the smallest particles forming the broad, sweeping dust, tail, and the larger, heavier grains falling behind. But that does not account for the sheer coherence and longevity of the anti-tail observed in 3I Atlas. The Arend-Roland event was a brilliant but transient feature. The anti-tail of 3I Atlas appears to be a permanent fixture, a constant companion in its journey. This suggests not a sporadic release, but a continuous, regulated emission of specific materials. What if the particles constituting this anti-tail are not merely passive gravel, but possess intrinsic properties that grant them a more active role in the comet's dynamics? This leads us to a more speculative hypothesis. Imagine that within the coma of 3I Atlas, the anti-tail is not composed of random debris, but of a specific population of large ice grains, some the size of small pebbles. These are not simple lumps of frozen water, they are spinning. As volatile ices sublimate from their surfaces in the Sun's heat, they do not erupt symmetrically. Imperfections in their structure create natural nozzles, jetting out gas in specific, fixed directions relative to the grain's axis of rotation. Each grain becomes a microscopic piston engine, a primitive but effective thruster. The collective, aligned thrust from billions of such grains, all contributing a minuscule force, could sum to a significant and continuous pressure on the nucleus itself. This would not be the violent, explosive outgassing that cracks the comet's surface, but a gentle, sustained push from a cloud of micromachines operating just ahead of the nucleus. The anti-tail, then, would be the visible manifestation of this engine's exhaust plume, or perhaps even its fuel reservoir. Is the coma of 3I Atlas not just a cloud of vaporized ices, but a diffuse, distributed propulsion system? Let us analyze the mechanics of such a system. First, the presence of large grains increases the inertia of the outflowing cometary material. A coma rich in pebble-sized ice has more mass, more momentum. According to current models, this would simply make the coma denser and the dust tail brighter. However, the stability of the anti-tail suggests something more, a conservation of directional force. The particles are not just large, they are maintaining a specific orientation, a sheet-like structure that holds its form against the dissipative forces of the solar wind and radiation. This implies a level of coordination that random ejection cannot explain. Secondly, the system of gas and dust may be phase-locked. The outgassing from the nucleus lifts the grains. The grains, in turn, with their piston engine thrust, modulate the flow of gas around them, creating a feedback loop that stabilizes the entire structure. This natural guidance system could subtly steer the comet, making minute adjustments to its trajectory over long periods. The anti-tail is the rudder, and the large ice grains are the crew silently adjusting its trim. Could the seemingly chaotic coma of a comet conceal a self-regulating hydrodynamic system of astonishing complexity? The implications of this are profound, reaching beyond celestial mechanics into the future of human exploration. If a natural body, like 3I Atlas, utilizes a dust-ice propulsion mechanism, it presents a blueprint for a new class of spacecraft engine. Imagine a nanosatellite, a CubeSat, equipped not with bulky fuel tanks and complex plumbing, but with a reservoir of water ice and a system to eject and spin microscopic ice grains. Solar energy would power the sublimation, turning each grain into a tiny, controllable thruster. This would be an engine of immense longevity and fine control, capable of adjustments measured in millimeters per second over years, perfect for long-duration interstellar precursor missions. The comet teaches us that propulsion need not be a violent, concentrated burn, but can be a patient, distributed force. Are we then on the cusp of learning to harness the very forces that drive these ancient travelers to build engines in the image of a comet's ghostly anti-tail? Yet, any propulsion system, natural or engineered, must express its effect through motion. For an object like 3I Atlas, its path is not a simple arc around the Sun, but a hyperbola, a trajectory that speaks of an origin beyond our solar system. Its velocity is measured in tens of kilometers per second, a speed that renders its passage through our system a fleeting event. At such velocities, the geometry of its path becomes exquisitely sensitive. A minute change in angle, a tiny perturbation induced by a sustained, gentle force near a massive body like Mars, would not merely adjust its course within our system. It would fundamentally alter its ultimate destination, redirecting it onto an entirely new hyperbola aimed at a different point in the galaxy. The frame of reference from which we observe it would shift, changing its apparent path and velocity from our earthly vantage point. The smallest nudge at the right moment can rewrite an object's cosmic destiny. If a distributed propulsion system were indeed active within 3I Atlas, how would its subtle, continuous thrust manifest in the precise geometry of its interstellar trajectory? Consider the trajectory, a perfect hyperbola etched onto the celestial sphere, a path defined by a single, immutable point of closest approach to our Sunday. It is a line drawn by the universe itself, a gateway through our system that is entered but once. The mathematics are precise, the orbital elements calculated to a staggering degree of accuracy. Yet, what if that line is not perfectly drawn? What if, upon its arrival, the object designated 3I Atlas exhibited a minute deviation, a perturbation of a mere fraction of a degree in its inbound course? According to current models of celestial mechanics, such a minuscule angular shift at perihelion, the point of its closest solar encounter, would be statistically negligible, lost in the noise of observational uncertainty. It would be attributed to the limitations of our instruments, a rounding error in the grand calculation. But what if that error was not an error at all? What if that tiny, almost imperceptible nudge was the entire point? A deliberate course correction, so subtle that it masquerades as instrumental noise, yet with consequences that cascade across light years, rewriting its entire future journey through the galactic void. If a billiard ball strikes the cushion of a table at a slightly altered angle, its path across the felt is irrevocably changed. Could 3I Atlas be such a cosmic projectile, Having glanced against an unseen cushion at the edge of our solar billiard table, its trajectory intentionally altered for a purpose we cannot yet fathom. The evidence for this lies in the unforgiving nature of hyperbolic orbits. An object on a closed, elliptical path is bound to the Sun. Its errors and anomalies are local, repeating with each orbit. But for a hyperbolic traveler, every action is cumulative and final. Its velocity, measured in tens of kilometers per second, is its terminal velocity. A small angular deviation at such speeds does not merely result in a slightly different path. It is magnified over time and distance into a chasmic gulf. A shift of a few arc-seconds at perihelion could project its predicted position years later into an entirely different constellation, moving it from a field of empty space to a direct line of sight with a specific, perhaps significant, star. Furthermore, on an open orbit, any non-gravitational acceleration, be it from outgassing, solar radiation pressure, or something else entirely, does not merely perturb a repeating cycle. It integrates directly into the object's outgoing velocity vector, a permanent addition to its cosmic speed, a one-time boost applied at the precise moment it slingshots away from our Sunday. The very geometry of its passage turns minor forces into major directional changes. So, we must ask, was its passage through our inner system merely a gravitational assist, or was it a carefully calibrated refueling and course correction maneuver, using our Sun's energy and perhaps even our own observational biases as tools? Let us then analyze the implications of such a deviation, scaling its consequences from the practical to the profound. A minor deviation, on the deviation order of a few hundredths of a degree, would primarily affect our own calendars. It would shift the optimal windows for observation by our most powerful telescopes, like the James Webb, by days or weeks. A target once perfectly positioned for spectroscopic analysis in late 2025 might now require a recalibrated observing schedule for early 2026. A minor logistical headache for astronomers, but nothing more. Or is that merely the most superficial consequence, a deliberate tweak to test our response time and observational flexibility? A moderate deviation, perhaps a few tenths of a degree, introduces a more fundamental shift. As 3I Atlas recedes, its position against the backdrop of the Milky Way would be fundamentally altered. The stellar background against which we measure its reflectivity, its composition through spectroscopy, and its final velocity would be completely different. The data we collect would tell a different story, not because the object has changed, but because our vantage point for studying it has been repositioned. It would be like reading the same book but under a different colored light, revealing new nuances and obscuring old ones. What information is encoded not just in the object itself, but in the specific context of the stars it passes in front of as it leaves? Was its path fine-tuned to ensure it was silhouetted against a particular type of star, allowing for a specific spectroscopic analysis we have not yet thought to perform? The most extreme scenario, born from a larger deviation or an unanticipated non-gravitational acceleration, is the most haunting: the premature loss of visual contact. The object, smaller and darker than anticipated, could fade from the view of our optical telescopes much sooner than predicted. It would vanish into the blackness, leaving only the faintest of thermal signatures for infrared space telescopes to chase, or requiring the immense power of planetary radar systems like the Deep Space Network to ping it, a lonely echo in the dark. We would be left with only the most basic data, a rough trajectory, and a residual heat profile, a ghost in the machine of our solar system. Is the ultimate purpose of such a precise trajectory to ensure a controlled and timed disappearance, to leave us with just enough data to know it was here, but not enough to truly understand it, thereby guaranteeing its mystery and our enduring obsession? The ultimate legacy of 3I Atlas, therefore, may not be the object itself, but the paradigm shift it forces upon our methods of observation. Its passage will likely establish a permanent, hyperbolic window protocol within the global network of telescopes. No longer will we treat such visitors as passive rocks on a predetermined path. We will monitor them in real time for any minute course alterations, treating their entire passage as a dynamic event, not a static observation. Every fluctuation in brightness, every spectral line, every tiny deviation from the ephemeris will be scrutinized as potential evidence of activity, of intelligence, or of physics beyond our current grasp. But can a network of telescopes built to find answers ever truly be prepared to document a phenomenon whose primary characteristic is its ability to redefine the questions? This naturally compels a comparison with the two previous enigmatic visitors, Oumuamua and Borisov. They were the first scouts, each presenting an extreme and puzzling nature. Oumuamua was a dry, elongated object, exhibiting a non-gravitational acceleration without any visible coma or outgassing, a tumbling shard of unknown composition that defied easy classification. Borisov, in stark contrast, was a textbook comet in its activity, a familiar yet alien visitor spewing water vapor and cyanogen gas, a pristine relic from another star system. They represented two ends of a spectrum, one utterly anomalous, the other deceptively familiar. Where, then, does 3I Atlas fall on this spectrum? It appears to be an intermediate case, a hybrid that further complicates the narrative. Early data suggests it possesses the solid, cohesive structure of an asteroid, yet it also displays faint, intermittent signs of volatile outgassing, a whisper of activity that Oumuamua possessed, but Borisov shouted. Is this blending of properties merely a coincidence, a middle point in a natural distribution of interstellar objects, or is it a deliberate synthesis, a refinement of design based on the data gathered from the passages of its predecessors? In the vast, silent ocean of interstellar space, the first known travelers from distant star systems arrived in quick succession, each a cryptic message in a bottle cast adrift by cosmic tides. The first, Oumuamua, discovered in October 2017, was a dry, elongated shard of rock and metal, tumbling end over end through our solar system without the faintest whisper of a comet's tail. Then, just under 2 years later, in August 2019, Borisov entered the stage, a quintessential comet erupting with volatile ices and enveloped in a sprawling cloak of dust. They presented themselves as two stark opposites, two fundamental archetypes, the barren asteroid and the volatile comet. This binary understanding, however, was destined to be short-lived, for the cosmos is a place of nuance and transition. The subsequent arrival of the third interstellar object, designated 3I Atlas, did not conform to this simple duality. It was neither as desiccated as Oumuamua, nor as floridly outgassing as Borisov. Instead, it occupied a mysterious middle ground, a symphony composed of both rock and ice, forcing us to reconsider the very nature of these celestial nomads. Could it be that we are witnessing not just random wanderers, but distinct lineages, each a signature of its own alien stellar nursery? According to current models of planetary formation, the stark difference between Oumuamua and Borisov can be four, explained by the location of their birth within their respective protoplanetary disks. An object forming close to its star, within the so-called snowline, would be composed primarily of rock and metal, baked free of volatile materials, much like the planets of our inner solar system. This would account for Oumuamua's inert and rocky nature. Conversely, an object forming in the colder, outer reaches of a system, beyond the snowline, would be a primordial mixture of ices and dust, a classic comet, exactly as Borisov appeared to be. This simple, elegant model neatly categorizes the first two interstellar visitors, placing them at opposite ends of a compositional spectrum. It suggests that our solar system's own division between rocky asteroids and icy comets is a universal standard, a predictable outcome of physics repeated around countless stars. Yet, This comfortable classification begins to fray when confronted with an object that defies such clear-cut boundaries. However, the intermediate nature of 3I Atlas presents a profound anomaly that challenges this binary perspective. Its activity level was subdued, a slow, steady release of gases rather than the dramatic outbursts characteristic of Borisov. Yet it undeniably possessed volatile ices that Oumuamua conspicuously lacked. This forces a more speculative hypothesis. What if we are not merely seeing objects from different regions of a disk, but from entirely different classes of stellar systems? Imagine if Oumuamua, Borisov, and 3I Atlas are representatives of three distinct families of interstellar objects. The first family, the dry, rocky asteroids, could be the shattered remnants of terrestrial planets from systems rich in heavy elements, perhaps orbiting aging red dwarfs where gravitational dynamics are fiercely chaotic. The second family, the volatile-rich comets, might be the pristine, unaltered building blocks ejected from young, massive stellar nurseries, their ices preserved in deep freeze for eons. And the third, the hybrid objects like 3I Atlas, could originate from a very specific and perhaps rare environment, a system where the snowline migrated dramatically inward during its early history, coating rocky bodies in a mantle of ice, or from the outer regions of a binary star system where complex gravitational shepherding creates bodies of mixed composition. Are these three visitors not random individuals, but emissaries from three fundamentally different galactic lineages? The evidence supporting this radical reclassification lies in the detailed analysis of their behavior. Oumuamua's most enduring mystery was its non-gravitational acceleration. As it departed our Sun, it sped up slightly, a change that could not be attributed to gravity alone. The mainstream explanation points to outgassing, the sublimation of ices, turning directly to gas, acting as a natural rocket engine. Yet, no coma, no tail, no dusty envelope was detected around it. Scientists suggested this could be due to the outgassing of highly volatile ices like solid hydrogen or solid nitrogen, which would not drag dust grains with them, or that the object was so aged and porous that its outgassing was a faint, diffuse process. This remains a plausible, if unproven, interpretation based on known physics. But that does not account for the sheer strangeness of its shape, inferred from its extreme brightness variations, or the possibility that its acceleration mechanism was something entirely other. This opens the door to a more unsettling possibility. What if the acceleration was not from outgassing at all, but from the subtle pressure of solar radiation on an object of extraordinary geometry, a light sail of natural, or perhaps unnatural, origin? The required density for such an effect is incredibly low, suggesting a structure more fractal than solid, a cosmic foam. If this were the case, then Oumuamua was not a planetesimal fragment but something else entirely, a manufactured artifact or a piece of exotic debris from a cataclysm we cannot yet imagine. Could its dryness be a sign not of formation inside a snowline, but of a history so violent that all its volatiles were scorched away in an instant? Borisov, in stark contrast, was a textbook comet in its dynamics, its outgassing accompanied by a dense cloud of dust and carbon monoxide, its behavior so familiar it felt almost like a local citizen briefly visiting from a neighboring stellar province. Its trajectory and composition were perfectly explained by its origin in the cold outer disk of a common M-dwarf star system. Yet, its very normality, when placed next to the profound abnormality of Oumuamua, is itself an anomaly. Why would one interstellar object be so bizarre and the next so utterly conventional? It is within this chasm of contradiction that 3I Atlas finds its significance. Its intermediate activity level suggests a body that is neither purely rocky nor overwhelmingly icy. Dynamically, it too exhibited a slight non-gravitational push, but one that was accompanied by faint, detectable signs of outgassing, bridging the gap between the inexplicable acceleration of Oumuamua and the classical cometary jetting of Borisov. This intermediate dynamic points toward a hybrid composition. Perhaps it is a rubble pile aggregate that incorporated both silicate rocks and pockets of water ice, a testament to a more turbulent and mixed formation environment than either of its predecessors. Its very existence argues against a simple two-category classification, and instead paints a picture of a galaxy teeming with a far richer diversity of minor bodies than we had ever anticipated. What if the three objects represent a chronological sequence? A dry, ancient population from the galaxy's early epochs, a volatile, rich population from ongoing star formation, and a mixed population from systems in a specific, transitional phase of their evolution. The implications of this tripartite scheme are profound, reaching far beyond mere taxonomy. If these objects are indeed direct samples from other star systems, then each one is a Rosetta Stone for decoding the chemical and physical conditions of its home. By analyzing their spectra, their density, and their activity, we can perform a form of galactic archaeology, working backwards to infer the composition of their parent protoplanetary disks. Oumuamua's refractory-rich nature might tell a story of a system with a high metallicity, perhaps one that formed many terrestrial planets. Borisov's abundance of carbon monoxide could indicate it hailed from a cold, carbon-rich environment around a cool star. And 3I Atlas, with its balance of rock and water ice, could be the key to understanding how water is delivered and distributed across different types of planetary systems. This is not merely the study of a few random rocks. It is the beginning of a new field of comparative planetology on a galactic scale, where these objects are our first physical probes into the building blocks of exoplanets. But if each object is a unique signature, how many more families are waiting to be discovered, and what will they tell us about the prevalence of conditions suitable for life across the Milky Way? To answer such a question, our perspective must shift. Our earthbound telescopes, peering through the thick, turbulent blanket of our atmosphere, offer a limited and distorted view. The faint, fleeting signals from these interstellar interlopers are easily lost in the noise. To truly begin this census, to classify and understand the river of stones flowing between the stars, we require a clearer, more stable vantage point, a platform far removed from our planet's obscuring shroud. We must look not just from our world, but from another. This necessity leads our gaze outward, to our neighboring world, the red planet Mars. Orbiting it are three silent sentinels: the Trace Gas Orbiter, the Mars Reconnaissance Orbiter, and Mars Express. These robotic platforms, with their powerful cameras and spectrometers, are more than just tools for studying Mars. They are, in effect, a mobile astronomical observatory positioned on the far side of Earth's atmospheric interference. From their unique orbital paths, they can track these interstellar visitors with a clarity impossible to achieve from the ground, providing a parallax view that can precisely triangulate their trajectories and dissect their chemical composition without the blurring effects of air and water vapor. They represent the next logical step in this grand investigation, turning our solar system into a multi-platform sensor array. Could it be that the future of interstellar astronomy lies not on the Earth's surface, but in the silent, vacuum-clear skies above Mars? Mars, the red planet, has long been a destination for our robotic explorers, a world of stark beauty and profound questions. Yet, we are now beginning to perceive it as something more, a platform of profound utility. It is transforming from a mere object of study into a unique vantage point, an observatory beyond Earth. For nearly 2 decades, our mechanical emissaries have been silently preparing for this role. Since 2003, the Mars Express orbiter has circled the rust-colored globe, its instruments probing the atmosphere and soil. It was joined in 2006 by the Mars Reconnaissance Orbiter, its powerful camera mapping the terrain in exquisite detail. And since 2018, the Trace Gas Orbiter has begun its meticulous work, sniffing the thin Martian air for the faintest chemical whispers. These are not isolated missions, they are the foundational infrastructure for a new eye in the cosmos. From its position further from the Sun than Earth, Mars offers a parallax view of the universe, a different perspective on cosmic phenomena that a single planet, no matter how well instrumented, could never achieve alone. What if the true purpose of our colonization of Mars is not merely to understand the planet itself, but to use it as a stepping stone to comprehend the greater cosmos? This nascent capability invites a more audacious vision, a fiction born from the seeds of current engineering plans. Imagine a network, not of individual telescopes, but of entire worlds working in concert. By the 2030s, we could be on the cusp of establishing a true interplanetary interferometer. This would be a system where radio antennas on Earth, on Mars, and perhaps on spacecraft stationed at the gravitational balance points between them, all turn their collective gaze towards a single point in the sky. The combined baseline of this network would be not thousands of kilometers, but hundreds of millions, effectively creating a single telescope dish the size of the inner solar system. The resolving power of such an instrument is almost unimaginable, capable of discerning details on the surfaces of distant exoplanets, or peering into the violent hearts of active galactic nuclei. The concept is rooted in the established principles of very long baseline interferometry, but scaled to a level that redefines the possible. Could humanity's first great collaborative project on an interplanetary scale be the construction of an instrument of pure observation, a machine to see the unseeable? The practical data already streaming from our Martian orbiters provides the initial, tangible evidence for the value of a second viewpoint. These spacecraft provide a different geometric baseline for observation, a fundamental shift in position that reduces the inherent ambiguities in tracking the trajectories of distant objects. When observing from Earth alone, the precise path of an interstellar interloper through our solar system can be difficult to pin down. Its distance and speed are inferred from its apparent motion against the stars. But with a second set of eyes on Mars, we can perform a simple triangulation, instantly refining its three-dimensional trajectory with far greater precision. Furthermore, the ability to conduct observations across the spectrum from ultraviolet through visible light and into the infrared from two distinct vantage points allows for a powerful form of stereoscopic analysis. It enables us to separate the faint directional jet of outgassing from a comet's nucleus from the more diffuse glow of sunlight simply scattered by its dust cloud. This dual perspective spectroscopy is the key to diagnosing the true nature of these visitors. If we can so easily refine our understanding with just 2 points of view, what profound secrets might we unlock with a third or a fourth? The analytical power of this approach unfolds in a logical, escalating sequence, each step building upon the last to reveal ever deeper layers of information. The first and most straightforward application is the power of two eyes. With observatories on Earth and Mars simultaneously tracking an object, we achieve precise triangulation of its orbit. This is celestial cartography at its most fundamental, allowing us to chart the visitor's path through the solar system with an accuracy previously reserved for local asteroids and comets. We can determine not just where it is, but where it has been and where it is going, with a new degree of certainty, distinguishing between an object on a simple hyperbolic orbit and one that may be exhibiting the faintest, most telling deviations. Is its path purely dictated by the gravity of the Sun and planets, or is there a subtle, additional force at play? Building upon this, the second level of analysis emerges from the synergy of multiple observational platforms. With several instruments, perhaps a camera on Mars Reconnaissance Orbiter, a spectrometer on the Trace Gas Orbiter, and the full battery of Earth's telescopes all focused on one target, we can begin to resolve ambiguities that plague single-point observations. A key challenge is deciphering the rotation and any potential jet activity of a small, faint body. From Earth, the changing brightness of an object can be due to its spin, its irregular shape, or localized outgassing. But with simultaneous observations from two widely separated locations, these effects can be disentangled. The light curve appears different from Mars than from Earth, allowing scientists to model the true rotation period and axis, and to isolate the specific signature and location of any jet. This tells us not just about the object's trajectory, but about its dynamics and activity. If we detect a jet, is it a simple release of volatile ices, or is it something more structured, more controlled? This progression leads inexorably to the third and most profound level, the interplanetary network. The ultimate expression of this concept is not merely simultaneous observation, but phased array interferometry across the void. By linking radio telescopes across the Earth-Mars divide, we could measure the time delay of a signal arriving from a distant cosmic source with picosecond precision. This goes beyond imaging. It is a direct measurement of the fabric of space-time along the path of the light. Such a network could detect the minute ripples in space-time caused by gravitational waves from merging supermassive black holes, or test the effects of solar gravity on light with unprecedented accuracy, probing the very limits of general relativity. It would, in essence, turn the solar system into a laboratory for fundamental physics. What subtle distortions in the light from a distant quasar would reveal the presence of a gravitational wave too faint for any terrestrial instrument to hear. The culmination of this endeavor would be the birth of an entirely new discipline, interplanetary astronomy. This is not merely an extension of our current capabilities, but a qualitative leap. It would provide the foundational framework for all future encounters with interstellar objects, the 3 is that are now understood to be passing through our system with some frequency. With an interplanetary network in place, the next Oumuamua, or Borisov, would not be a fleeting, enigmatic mystery. It would be an object of intense, multi-perspective scrutiny from the moment of its detection. Its trajectory, composition, rotation, and activity would be characterized in detail, leaving far less room for speculation and far more for definitive analysis. This network would become humanity's standard protocol for greeting visitors from other stars. Will the first definitive evidence of extraterrestrial technology not be a radio signal, but a high-resolution interferometric image of an anomalous object captured by the combined eyes of two worlds? The data that fuels this new astronomy, particularly from the Martian perspective, comes from sophisticated instruments like the Nomad and Omega spectrometers aboard the Trace Gas Orbiter and Mars Express. These devices do not take pretty pictures. They dissect light into its constituent colors, revealing the chemical fingerprints of the materials it has interacted with. When an interstellar object passes near Mars, these spectrometers can capture the infrared light reflected from its surface or emitted by its coma. This infrared spectrum is a treasure trove of information, allowing us to trace the presence of evaporating volatiles. The critical question becomes, what exactly is sublimating into the vacuum? The answer, locked in the specific absorption lines and emission bands of the spectrum, carries profoundly different implications for the object's origin and nature. Is the dominant volatile simply water ice, the most common frozen substance in the cosmos, indicating a fairly conventional, if extrasolar, icy body? Perhaps the data reveals a strong signature of carbon dioxide ice, a compound common in the outer reaches of planetary systems. This would suggest an origin in the cold, distant cloud of planetesimals, surrounding the object's parent star, a place where carbon dioxide can condense. Its presence would map the object to a specific thermal environment in its home system, a clue to its birthplace. But what if the spectral analysis reveals something more complex, the subtle signatures of organic molecules? These are not necessarily indicators of life, but rather of prebiotic chemistry, the building blocks from which life can arise. Methane, methanol, or even more complex carbon chains would indicate that the object is not a pristine ball of ice, but a body that has undergone a degree of chemical evolution. It would suggest that the processes that create the precursors to life are not unique to our solar system, but are a universal phenomenon. Does the presence of such compounds on an interstellar traveler imply that the seeds of chemistry that led to us are scattered throughout the galaxy? Each type of volatile carries a different story, a different meaning about the celestial body's origin and history. A spectrum dominated by water ice points to a formation similar to comets in our own Oort cloud. A spectrum rich in carbon dioxide might hint at a birthplace in a system with a different chemical composition or thermal structure than our own. And the detection of complex organics would be a revolutionary discovery, suggesting that the fundamental chemistry of life is a common outcome of cosmic processes. The Nomad and Omega instruments are thus not merely chemical sensors. They are forensic tools for interstellar archaeology, capable of reading the hidden history of a wanderer from another star. As we decode these spectral lines, are we merely analyzing chemistry, or are we reading the first pages of a galactic history book, one that describes the prevalence of life's ingredients across the light years? The data from the red planet provides a unique chapter, but the full story awaits the next turn, the next anomalous signal that challenges our understanding of what is possible. The silent, watchful eye of the Nomad spectrometer, orbiting Mars aboard the Trace Gas Orbiter, does not see worlds, but words. It reads the universe in the language of light, dissecting the faint glow of the Martian atmosphere into its constituent colors. Each absorption line, each dip in the spectrum, is a character in a cosmic alphabet. For years, the story it has told has been one of familiar, if sparse, chemistry. The signatures of water vapor, the dominant breath of carbon dioxide, the trace whispers of carbon monoxide. A narrative dictated by the known laws of planetary science. But after the hypothetical event, the anomaly, the lexicon, has changed. The task now, in the wake of that moment, is to reassemble these spectral letters, to read the new sentence that has been written across the Martian sky. It is a sentence that appears to be structured, a syntax of elements that defies random chance, pointing towards the target of the campaign designated 3I Atlas. Could it be that we are not merely analyzing chemistry, but deciphering a message encoded in the very building blocks of a world? According to current models, the spectral data returned by instruments like Nomad and its predecessor, Omega, on Mars Express, which has been faithfully mapping the mineralogy of the red planet since 2003, should reflect the predictable interactions of solar radiation with molecules in the atmosphere. The presence of water suggests a gentle, persistent process, perhaps the slow sublimation of subsurface ice, a soft and steady jet of vapor into the thin air. The dominance of carbon dioxide is the baseline, the constant exhalation of Mars itself. Even the intermittent spikes of carbon monoxide can be rationalized through photochemistry, the breaking apart of carbon dioxide molecules by ultraviolet light, a violent but well-understood reaction that produces a powerful, if short-lived, jet of gas. These are the established paragraphs in the story of Martian atmospheric science, a story written over decades of observation. But what if, hidden within this familiar text, there was a footnote written in a different ink? The data streams following the event contain more than just the expected compounds. There are faint, yet persistent, spectral lines that correspond to complex organic molecules. These are not the simple carbon-based compounds we have found before, but more intricate structures, chains, and rings of carbon atoms bonded with hydrogen, oxygen, and nitrogen. The mainstream explanation would point to abiotic processes, the result of complex chemistry, on dust grains, or in the tenuous atmosphere, a narrative of chance and necessity on a sterile world. Yet, the specific arrangement, the peculiar ratios, and the timing of their appearance alongside the other anomalous jets challenges this comfortable conclusion. These spectral signatures resemble not random chemical noise, but a coherent signal, a biological profile slumbering within the data. Are we witnessing the dormant chemical blueprints of life, a ghostly fingerprint that has been stirred from its ancient sleep and now drifts between the stars? The evidence for this is rooted in the very bedrock of our methodology. The NOMAD instrument, in its scientific operation since 2018, and the foundational IR data from Omega were designed for this precise purpose, to trace the subtle fingerprints of water, carbon dioxide, and carbon monoxide with unparalleled sensitivity. The important scientific milestones recorded in 2020, which refined our understanding of Martian atmospheric loss, and the new data from 2024 and 2025, provide the crucial before and after snapshot. The analysis is revealing a compelling correlation. The gentle, persistent water jet seems to act as a background carrier, a steady stream. The powerful, intermittent bursts of carbon monoxide and carbon dioxide appear as punctuation, sharp exclamations that disrupt the flow. And intertwined with these, the organic traces exert a subtle influence, as if their presence alters the cohesion of particles, the very dynamics of the jet. They are not mere passengers, but seem to be an integral part of the propulsion mechanism itself. This leads to a profound and unsettling inference. If these complex organics are confirmed, they are not native to Mars. They are a delivery, a chemical parcel of interstellar origin. Their sophistication suggests they were not forged in the turbulent cradle of a young solar system, but in the cold, dark molecular clouds that drift between the stars, the nurseries of complexity that pervade the galaxy. The presence of such a package, delivered so precisely to the Martian system, implies that the supply chain for the molecular precursors of life is not a local phenomenon, but a universal constant. The universe, it seems, is preloaded with the ingredients for biology, and it has a delivery system. But who, or what, is the intended recipient? The spectral lines are a Rosetta Stone, but the translation is only half complete. We have decoded the chemical words, but to understand the sentence, we must see the speaker. We must turn from the abstract language of light to the concrete reality of imagery. What form does this natural engine take, and what visual testimony does it leave behind? The answer begins to materialize not in spectra, but in pixels. High-resolution images from the Martian orbit, a continuous sequence captured in the days following the spectral anomaly, reveal a faint, ethereal halo surrounding the object. It is not a symmetrical shroud, but a lopsided glow, a veil of fine particles and ionized gas that streams away, leaning persistently to one side. This is not the random outgassing of a simple icy body warming in the sun. This is direction. This is purpose. The halo's asymmetry is the signature of a nozzle, a natural focusing of volatile gases into a coherent jet. It is the visual proof of the natural engine hypothesis, the mechanism that transforms a passive comet into a guided vessel. The spectral data told us of the chemistry of the thrust. These images show us its geometry, its vector. They confirm that the outgassing is not a death rattle, but a controlled breath. Scientists suggest this could be due to a unique geological feature on the object's surface, a fissure or a cavern with a specific morphology that naturally collimates the escaping gases, much like a rocket nozzle shapes exhaust. The dominance of carbon dioxide and carbon monoxide, with their high volatility, provides the powerful, if intermittent, thrust, while the steadier water vapor jet offers a constant, fine-tuned adjustment. This combination of impulsive and continuous forces would allow for a surprising degree of control over the object's trajectory. The known laws of physics can readily account for such a phenomenon. We have, after all, engineered similar principles into our own spacecraft, but that does not account for the orchestration. A naturally formed nozzle is one thing. The precise chemical mixture required to produce the observed spectral signature and the corresponding thrust profile is another. The presence of complex organics, acting as a surfactant or a catalyst within the jet, suggests a level of chemical engineering that blurs the line between a natural comet and a designed object. The intermittent bursts of carbon monoxide are too perfectly timed, too efficient in their conversion of solar energy into kinetic force. It is as if we are not looking at a random rock, but at a machine whose components are chemistry and geology, an engine carved not in a factory, but by eons of cosmic evolution, or perhaps by intelligence that thinks in geological time. Could the very concept of a machine be a human conceit, blinding us to forms of technology that are grown rather than built? The confluence of evidence is now overwhelming. The spectral alphabet from Nomad spelled out a complex, delivered chemistry. The orbital images from this campaign reveal the physical mechanism of its delivery. A directional jet, a natural engine. Together, they paint a picture of an object that is not merely tumbling through space, but navigating it. The water provides the gentle, constant thrust for course corrections. The explosive bursts of carbon monoxide provide the powerful impulses for major maneuvers. And the organic molecules, the biological profile, are the key that ties it all together, the sophisticated payload that hints at a function beyond mere travel. This is not a simple delivery, it is a targeted insertion. The implications redefine our place in the cosmos. If this is true, then the emergence of life on Earth was not a singular miracle. It was an event on a cosmic schedule, facilitated by a galactic logistics network that operates on million-year timelines. The universe is not only habitable, it is inhabited, not necessarily by creatures in ships, but by ideas encoded in chemistry, by biological templates that drift between the stars, seeding worlds with potential. We on Earth may be the product of such a delivery, our own biology, perhaps a chapter in a story that began light years away. The arrival of 3I Atlas, then, is not an invasion, but a supply drop, a reminder that we are part of a larger, interconnected biosphere that spans the interstellar void. But what is the ultimate source of this cosmic supply chain, and what, precisely, is the blueprint that has been delivered to our doorstep? A close-up image from Martian orbit. At first glance, it appears to be yet another piece of the vast, silent mosaic of data we collect from our robotic sentinels. A solitary comet, designated 3I Atlas, drifts against the black velvet of interplanetary space. But if each frame of data is a single breath, a time-lapse sequence from the orbit of Mars has captured a most peculiar anomaly. 3I Atlas appears to be breathing irregularly. The faint, ethereal glow of its coma, the cloud of gas and dust enveloping its nucleus, does not swell and recede in perfect synchrony with the warmth of the distant Sunday. There is a hitch in its rhythm, a subtle, persistent asymmetry that defies the simple, predictable physics of solar heating. It is as if we are witnessing not just a frozen relic passively sublimating, but an object with a hidden, internal cadence. According to current models of cometary behavior, the coma should be at its most expansive and brilliant on the side, facing the sun, where solar radiation is most intense, vaporizing ices and pushing dust and gas outward to form a tail. The observed phase lag, the delay in this expected brightening, could be attributed to thermal inertia within the comet's complex, porous structure. Scientists suggest this could be due to pockets of different volatiles, water ice, carbon monoxide, carbon dioxide, sublimating at different depths and rates, creating a complex and delayed response to solar energy, much like a dark rock warming slowly and radiating heat long after the sun has set. But what if the delay is not a product of chaotic internal chemistry, but of something far more structured? What if we are not looking at a random outgassing, but at a natural, cyclical engine, opening and closing with the comet's own rotation, venting gas not like a geyser, but with the mechanical regularity of an ancient water wheel turning in the darkness of interplanetary space? This would imply a level of geometric precision in its internal structure that current comet science has scarcely dared to contemplate. Could the very rotation of this interstellar visitor be governing a series of timed, directional vents? The evidence for this is etched into the sequential image data collected by our orbital assets around Mars. The narrowband and ultraviolet visible imaging modes, designed to isolate specific chemical signatures, reveal more than just a coma. They show a faint, lopsided halo, its brightest point consistently offset from the solar direction. Furthermore, the isophotos, the contour lines of equal brightness, do not form concentric circles. They are stretched, elongated along a fixed vector that remains constant across multiple Martian orbits, a stubborn directional preference in the vacuum of space. Most tellingly, the micro-variations in the comet's overall brightness oscillate with a precise period that matches the inferred rotation rate of the nucleus, the signature of a narrow, focused jet, sweeping across our line of sight like a lighthouse beam. One interpretation is that this halo is merely an artifact, a trick of the light and dust with no dynamical consequence. It is, after all, a tenuous cloud, exerting no measurable force on the comet itself. It is simply a visual curiosity, a complex pattern born from the interplay of sunlight and an irregularly shaped, rotating nucleus. Yet, if the jet is not merely a visual phenomenon but a genuine, albeit short-lived, expulsion of material with each rotation, it would be sufficient to leave its imprint upon the photometric data and, more significantly, impart a minute but cumulative acceleration. Each tiny puff of gas, ejected in a specific direction, would act as a miniature rocket thruster. The force would be infinitesimal, dwarfed by the gravitational pull of the Sun, but in the frictionless environment of space, even the smallest persistent force can build into a significant change over time. And if this jet is not just a sporadic sputter but a stable, cyclical feature, synchronized with the comet's spin, then the object transforms in our understanding. It ceases to be a simple icy dirt ball and becomes a natural reaction wheel, a gyroscopic jet engine. Each rotation, it pushes against the void in a preferred direction. This would not only explain the anomalous phase lag in its brightness, but could also apply a gentle, continuous torque, a force that could slowly, inexorably, bend the very direction of its escape from our solar system. Is the path of 3I Atlas being subtly steered by its own internal clockwork? This sequence of close-up images, therefore, becomes more than a collection of pictures. It is transformed into a diagnostic tool, a means to measure what we might call the reaction compass of an interstellar comet. By charting the fixed vector of its jet and correlating it with the minutest deviations in its trajectory, we can begin to reverse engineer the object's internal dynamics. This close encounter at Mars provides a template, a new observational paradigm for every future interception of such visitors. We are no longer just watching them pass by, we are learning to read their hidden rhythms. But how long can we continue to listen before the music fades? The window for such detailed observation is rapidly closing. By late October and November of 2025, 3I Atlas will have swung around the Sun and begun its journey back into the abyss. Its trajectory will carry it behind the Sun from our earthly perspective, placing it in a celestial blind spot where our most powerful telescopes cannot peer. The glare of our own star will render it invisible, a ghost retreating into the light. This final observational window, this last chance to gaze upon the object before it is lost to the solar glare, is therefore not merely an opportunity, it is an imperative. It is our only chance to verify the new orbital path, to see if the subtle nudges from its cyclical jet have indeed altered its course in a measurable way. The data we gather in these final weeks will either solidify this radical hypothesis or relegate it to the annals of intriguing but unproven anomalies. We will be able to compare its predicted position based on purely gravitational models with its actual location. Any discrepancy, however small, would be monumental. Mainstream astronomy would approach this final campaign with a focus on precision astrometry, pinpointing the object's exact position against the background stars with unprecedented accuracy. This is the bedrock of celestial mechanics. By doing so, we can precisely calculate its orbit and determine if any non-gravitational forces, perhaps even the gentle pressure of sunlight itself on its dust, are at play. This is the safe, proven path to understanding. Yet, the speculative mind wonders if the final glimpse of 3I Atlas will reveal something more. As it recedes, its jet, if it exists, will be pointing almost directly away from us. Will we see a final, telling fluctuation in its spectrum? A last, defiant puff of gas that confirms the cyclical engine theory just as it vanishes from view? The very alignment of its departure might offer a unique geometrical perspective to test the jet's stability and direction one final time. This is not just about verifying a trajectory, it is about confirming a mechanism. The implications stretch far beyond this single object. If 3I Atlas is indeed a natural reaction wheel, then we must ask what processes in the cold, turbulent nurseries between stars could forge such an object. Is it a fragment of a larger, engineered world, or is it a naturally occurring phenomenon, a new class of celestial body that our parochial experience within the solar system has never prepared us for? The answer lies in the precise measurement of its path, a path we can only trace until the sun claims it. What final secret will it impart before it is swallowed by the light, and will we be watching closely enough to understand it? The silence that follows its disappearance will be filled with the weight of our questions, and the data gathered in this last window will either be a key or a locked door. For when it passes behind the sun, it does not merely vanish from our view, it retreats into a realm of pure speculation, leaving us with only the echoes of its anomalous breath to ponder until, perhaps, another visitor arrives. But what if the next visitor is not so subtle? We are now approaching the final window. For a few brief weeks between October and November 2025, the trajectory of the object, known as 3I Atlas, will carry it behind the sun from our terrestrial vantage point. This is not merely a temporary occultation, it is a temporal gate that is closing, our last opportunity to gather decisive data before it recedes into the interstellar dark, potentially forever. This narrow gap in time presents a stark ultimatum. Either we confirm the anomalous course change, or we allow one of the greatest mysteries in human history to vanish in a final, solar glimmering silence. The clock is ticking down to a moment of profound consequence. Yet, what if this window is more than a simple consequence of orbital mechanics? The mainstream explanation is one of celestial geometry, a predictable alignment where the object passes within the sun's interference zone, its radio signals drowned out by solar plasma, its faint optical signature lost in the stellar glare. According to current models, this is an inevitable and temporary blind spot in our observational capabilities, a routine challenge in observational astronomy. We have faced such occultations with countless other bodies, from asteroids to human-made probes, and we simply wait for them to re-emerge. But that does not account for the peculiar synchronicity of this event with the object's own enigmatic rhythms. The window is not only narrow, it appears to be speaking, its opening and closing coinciding with a deeper, more fundamental cycle of the object itself, a pulse we are only beginning to discern. Could it be that this geometric coincidence is, in fact, a designed interval, a scheduled period of radio silence dictated not by the sun, but by the visitor? The very timing of our last look seems to be locked in a silent dialogue with the object's internal clock, suggesting a purpose to this concealment that we cannot yet fathom. What if we are not losing a signal, but are instead being deliberately placed in a state of waiting? Our ability to observe from Earth is already degrading, the elongation angle shrinking to a mere thread. The Doppler shift of its reflected light is becoming increasingly difficult to separate from the background noise of the solar wind. This is a problem of baseline. From a single point in space, our perspective is limited, our depth perception flawed. The solution, therefore, lies in a distributed eye. Space-based observatories, from the James Webb Space Telescope to the aging Hubble, and crucially, our assets in orbit around Mars, provide the most favorable baseline. They will remain in the game longer, their view less compromised by the sun's overwhelming presence. This is not a single observation, but a meticulously choreographed campaign. The schedule for deep imaging and spectroscopic analysis is locked into this optimal geometric window, a final, coordinated push to extract every possible photon of information before the curtain falls. We are aiming to capture not just its position, but its soul, its composition, its temperature, any outgassing, through a continuous, multispectral data set. We are attempting to record the object's final act before its solar intermission. But is this a final act, or merely the end of the first scene? The outcomes of this campaign branch into three distinct futures, each with its own profound implications. The first is a miss. Our instruments, for all their precision, fail to lock onto the target during the critical moment. Perhaps a solar flare corrupts the data, or a minor error in the ephemeris calculation points our telescopes at empty space. The consequence is not merely a lost data point. The object's trajectory model would freeze, its parameters forever locked with a high degree of uncertainty. Its future path becomes a widening cone of possibility, a ghost in the vastness. Could we ever find it again, or would it become a phantom, a tale of a missed opportunity told to future generations of astronomers? The second outcome is a hit. We successfully capture the data that confirms the non-gravitational course change. The Doppler shift in its spectrum, the precise astrometric measurements, all point to a force acting upon it that cannot be explained by the gravity of the Sun or the planets. This would be the moment of validation, the instant the interstellar object category is irrevocably changed from passive rock to active something. It would confirm that the forces shaping its journey are not those of a mere comet, but something else entirely. But what is the nature of this force, if not the gentle push of sublimating ices? The third, and most coveted outcome, is a complete capture. We secure a continuous, multispectral data set of sufficient duration and quality to lock down the mechanism of its propulsion. We see, in real time, the activation of a jet or the emission of particles from a specific region. The data would be so rich, so unambiguous, that it would point to a specific technology or a natural process hitherto unknown to physics. This would be the key that unlocks the door. But does humanity possess the intellectual framework to correctly turn that key, to understand the lock itself? The risk associated with a miss is existential for this field of study. If we fail, all long-term predictions dissolve. Every subsequent attempt to locate 3I Atlas after its solar passage would be a game of finding a needle not in a haystack, but in a cosmos of haystacks. The object, already small and dark, would be receding, its reflectivity potentially diminishing further. The great interstellar mystery would fade from a pressing scientific question into a historical footnote, a might have been. Are we prepared to let this story end, not with an answer, but with a fading echo? This leads us to a deeper, more fundamental question about the nature of the object itself. If we were to obtain that complete data set, what would it tell us about the traveler's origin? Is this an ancient comet, older than our solar system? The conventional hypothesis suggests that 3I Atlas is a planetesimal, a building block tossed from its native star system billions of years ago. Its composition, then, would be a pristine record of the protoplanetary disk from which it formed. According to current models of planetary formation, such a vagabond would be a time capsule, its chemistry frozen in the deep freeze of interstellar space, unaltered by the warmth of a star. Scientists suggest its surface would be dominated by water ice, carbon monoxide, and complex carbon-based molecules, a relic from the dawn of its own alien solar system. But what if its antiquity is of a different order? If 3I Atlas is truly that ancient, then every change in its behavior is a physical record of the environment of its formation, a diary entry from a distant, alien star system written in the language of physics and chemistry. The specific ratios of its isotopic abundances, the crystalline structure of its ices, the nature of the complex molecules on its surface, all of these would be a message from a place and time we can never visit. Yet, the anomalies we have already witnessed, its apparent lack of a coma and its sudden trajectory shift, defy this simple relic narrative. How does a simple, ancient ice ball learn to maneuver? This forces a more speculative hypothesis. Perhaps it is not a comet in any sense we understand. Perhaps it is something that has incorporated cometary material over its immense journey, using it as a cloak or a resource. Its age would then not be a measure of its passivity, but of its endurance. Each change in its behavior would not be a simple physical reaction, but a learned response, an adaptation honed over eons of travel through the galactic environment. The object would not just carry a record of its birth, it would carry the record of everything it has encountered since. Could we, in its present state, be seeing not its original form, but its current operational configuration? The data we hope to capture in that final window before solar conjunction may hold the answer. A detailed spectroscopic analysis could reveal isotopic ratios never before seen in our solar system, pointing unequivocally to an extrasolar origin. It could also reveal artificial elements or alloys with no natural explanation. The reflection spectrum of its surface might show a pattern that is too ordered, too structured, to be the product of random accretion. The very mechanism of its propulsion, if we can discern it, would be the ultimate clue. Is it the gentle, predictable jet of sublimating gas, or something else? Something that speaks of control and intent? As it swings behind the sun, what final secret will it impart, and will we be wise enough to understand it? The final window is closing, and with it, perhaps, our last chance to know if we are alone, or if we have simply failed to recognize the visitor for what it is. The apparition glides into the inner solar system, a silent, dark iceberg against the black velvet of space. Designated Comet Atlas, its journey is one of immense time and distance, but its true nature is only now beginning to dawn upon us. According to current models, comets are icy remnants from the formation of our own solar system, pristine time capsules from 4.5 billion years ago. Their compositions, their outgassing patterns, all speak of a local origin within the swirling protoplanetary disk that birthed our Sun and its planets. They are the leftover building blocks of our own cosmic neighborhood. Yet, from the moment of its discovery, Atlas presented a series of quiet, persistent anomalies. Its activity, the faint coma that signaled the sublimation of its ices, began at a distance from the Sun, so vast that it defied conventional expectations for a solar system comet. Its spectral signature was cold, alien, its light telling a story written in a different dialect of the cosmos. Could it be that we are not observing a local relic, but a visitor from a time before our Sun even ignited, a fossil from a foreign cradle? The mainstream explanation for such distant activity often points to the sublimation of exotic, highly volatile ices like carbon monoxide, which can turn to gas at the profound cold of the outer solar system. This is a plausible, even expected, mechanism for a Kuiper belt or Oort cloud object nudged inward by a gravitational perturbation. Scientists suggest this could be due to a surface covered in a layer of these supervolatile ices, responding to the faintest whisper of solar warmth. But that does not account for the spectral coldness, the peculiar color, the profound redness of its surface that speaks not of fresh, pristine ice, but of a landscape weathered by eons of exposure to cosmic rays and interstellar ultraviolet radiation. This is not the vibrant activity of a young comet, but the slow, deep exhalation of something ancient and profoundly tired. What if the ices we are witnessing are not merely exotic, but primordial, their very molecular structure a testament to conditions that have not existed in this galaxy for billions of years? This leads us to a more audacious hypothesis. What if Comet Atlas is not merely old in the context of our solar system, but is a true interstellar artifact, a fragment of a protoplanetary disk that coalesced around a star other than our Sun? It would be a cosmic nomad, a shard of ice and rock that has wandered the void between stars for epochs, carrying within its frozen heart the unaltered conditions of its birth. In this speculative framework, its low activity and coarse-grained dust are not signs of dormancy, but of extreme age. The ice within it has been baked and hardened by the relentless radiation of the galactic environment, becoming a super-durable matrix. Its spectral slope, that profound red, is the patina of deep time, the signature of a surface that has witnessed the birth and death of stars during its unimaginable journey. Is it possible that we are not looking at a comet, but at a flying black box, a cryogenic archive from a stellar nursery that vanished long before our Earth had even formed? The evidence, while circumstantial, is compelling. If we could measure the precise ratios of its outgassed molecules, the balance between water, carbon monoxide, and carbon dioxide, and find them to be starkly different from any ratio ever measured in a native solar system comet, the case for an extrasolar origin would strengthen dramatically. Such a chemical fingerprint would be a direct challenge to our parochial understanding of planetary formation. It would suggest that the processes which assembled our own world are not universal, that the recipes for building planets can vary significantly from one star system to another. The very laws of physics are constant, but their artistic expression in the form of cosmic chemistry may be infinitely diverse. Does the composition of Atlas hold a recipe for a world that never was, a blueprint for a planet that failed to form in its alien system? We must then consider the implications of its age, which can be interpreted on three distinct and increasingly profound levels. The first, and most conservative, is that Atlas is merely old on its surface. Its exterior has been heavily processed by its long journey, battered and irradiated, while its core may yet retain a more youthful, pristine composition, sealed away for billions of years. This is the model of a well-traveled object, its scars telling a story of a harsh journey, but its heart still holding its original secrets. The second interpretation posits that the comet is entirely ancient, a primordial body. Its internal structure, potentially revealing a pristine, layered, a stratigraphy, untouched by planetary heating or differentiation, would be a snapshot of a pre-planetary disk frozen in time. It would be a sample of the raw material from which entire alien worlds could have been built. But what if we dare to entertain the third, and most radical, possibility? What if Atlas is not just primordial but super ancient, a relic from the earliest eras of galactic star formation? This third hypothesis suggests that within its icy matrix, we might find isotopic ratios, or complex prebiotic organic molecules, that lie entirely outside any known frame of reference. The relative abundances of isotopes like deuterium to hydrogen, or specific forms of carbon, are thought to be signatures of a comet's formation region. A pattern that matches nothing in our solar system would be startling enough, but a pattern that suggests an origin in a population of stars much older than our Sun would be revolutionary. It would mean this object is not just a visitor from another star, but a messenger from a much earlier cosmic epoch, carrying chemistry that predates our entire solar system. Could its frozen core contain the molecular precursors to life that developed under a different sun, following a chemical pathway unknown to our own world? The opportunity presented by such an object is unparalleled in the history of astronomy. It is not merely a subject of study, it is a catalyst. A flying artifact of such potential value would inevitably ignite a new space race, not for territory, but for knowledge. The quiet, methodical work in observatories would be swiftly overtaken by the urgent need for a direct encounter. This would necessitate a leap in propulsion and miniaturized sensing technology, a mission to intercept and analyze this visitor before it departs our celestial neighborhood forever. The goal would be to fly past, or even rendezvous with, this ancient wanderer, deploying spectrometers of unprecedented sensitivity to read its chronological record, to taste its ancient ices, and decode its interstellar message. Are we, as a species, technologically and politically prepared to launch a mission to capture the story of a world that is not our own? This urgency is compounded by another of its enigmatic properties, its estimated size. Initial observations, based on its faint reflectivity, suggested a modest nucleus, but newer mass models, derived from its non-gravitational motion, the subtle pushes and tugs from its own outgassing, hint at an object that could be far more substantial than first predicted. A larger, more massive nucleus would possess a stronger gravitational hold on its own material. The jets of gas and dust that stream from its surface, which gently alter its trajectory, would need to be far more powerful than previously calculated to produce the observed deviations in its orbit. This forces a fundamental reconsideration of the energy powering its activity. Is the outgassing we see merely the faint, surface-level manifestation of a far more energetic process occurring deep within its core? The conventional understanding of cometary jets involves the sublimation of ices, primarily water ice, turning directly from solid to gas when heated by sunlight. This gas escapes, carrying with it dust particles, creating the coma and tails. The force of this escaping gas acts like a weak, natural rocket engine, subtly changing the comet's path over time. For a typical comet, the relationship between the observed outgassing and the resulting non-gravitational forces is well understood. But for an object with the suspected mass of Atlas, the math becomes problematic. The observed level of activity seems insufficient to produce the measured orbital changes. This discrepancy points towards either a serious miscalculation of its density or a source of jet propulsion that is more efficient or more forceful than simple solar heating can account for. Could the ices within Atlas be sublimating under pressure, or, through a different, more exotic mechanism than we have ever witnessed? One must then confront the more speculative implication of this mass discrepancy. If the nucleus is indeed larger and more massive, its internal structure could be complex, perhaps harboring sealed pockets of volatile ices under tremendous pressure. The release of this gas, through fractures or vents, would not be a gentle, steady flow, but a more violent, jet-like eruption. The energy required to initiate such eruptions might not come solely from the sunday. Could residual radiogenic heat from long-decayed radioactive isotopes, or even the release of chemical energy from exotic prebiotic reactions within its deep frozen interior, be providing an additional, internal power source? This would transform our view of comets from simple, passive, icy dirtballs into dynamic, geologically active worlds, even long after their formation. The very direction of its non-gravitational acceleration holds a clue. By analyzing the precise vector of this force, we can infer the location and persistence of its most active jet sources. A stable, long-lasting jet would suggest a single dominant vent, while a shifting, erratic force would point to a more chaotic and dynamic surface activity. For an object as potentially ancient as Atlas, the stability of its outgassing is a direct window into its structural integrity. Is the force that pushes it off its purely gravitational course the predictable sigh of a stable body, or the erratic coughs and sputters of a fractured, crumbling world? Its internal pressures finding new and unpredictable paths to escape? This interplay between its suspected great age and its puzzling mass creates a profound scientific tension. An ancient interstellar object should, by some logic, be a small, hardy survivor, a pebble that has withstood the trials of deep time. A large, massive object suggests a formation in a rich, resource-heavy environment, a place where significant accretion could occur. Can these two properties, great antiquity and substantial size, be reconciled? Or does the presence of both force us to reconsider what kinds of objects can be ejected from planetary systems and survive for billions of years in the interstellar medium? Perhaps our understanding of the durability of these icy planetesimals is fundamentally flawed, and the galaxy is populated with far more of these large, ancient wanderers than our models have ever predicted. As we watch its trajectory, refined by these mysterious non-gravitational forces, we are left to ponder the true nature of the engine within this dark iceberg. The observed outgassing is the visible symptom, but the cause, the driver of the pressure, remains hidden beneath a surface that has absorbed the light of forgotten suns. The gentle push that alters its path through the solar system is a force that has acted upon it for perhaps billions of years, a tiny, persistent thrust that has guided it across the light years until its path intersected with our own. What magnitude of explosive force, what sustained jet of sublimating primordial ice, is required to meaningfully alter the trajectory of an object that has accumulated such immense momentum from its epic journey through the galaxy? If the object designated 3I, Atlas, is indeed larger than our initial estimates, then the very nature of its observed non-gravitational acceleration becomes a far more profound puzzle. According to current models, such accelerations in comets are driven by outgassing, the sublimation of volatile ices into gas, which streams away from the nucleus, acting as a natural, if inefficient, rocket engine. For a small body, a modest diffuse jet can produce a measurable change in trajectory. But if 3I Atlas possesses a significant mass, the force required to alter its course must be not only powerful, but exquisitely precise, a delicate hand steering a colossus against the immutable pull of gravity. Could a simple, chaotic geyser of gas and dust truly execute such a finely tuned maneuver on a massive scale? The speculative hypothesis presents an intriguing alternative. What if the outgassing was not a broad, uncontrolled eruption, but a directed process? Imagine a vast, dark nucleus, its interior crisscrossed by a network of self-regulating capillary tubes, a natural plumbing system that opens its valves not at random, but at the precise moment and location dictated by the sun's angle. This would not be a simple jet, it would be a natural throttle, a feedback system where solar radiation itself governs the thrust. Such a mechanism would require a level of structural complexity we do not typically associate with inert celestial wanderers. Is it possible we are witnessing not geology, but a form of engineered geology? The data we possess offers tantalizing, if indirect, clues to its true scale. Its absolute magnitude was remarkably low, yet it did not fade as rapidly as one would expect from a small disintegrating object. This suggests a substantial radius, combined with an unusually low albedo, a vast, dark surface, absorbing nearly all the light that touches it. Furthermore, the small amplitude of its brightness, variation with phase angle, points toward a geometry that is nearly isotropic, a shape not dominated by sharp edges or dramatic concavities, but perhaps something more monolithic. From these subtle photometric signatures, we can infer that while the necessary force might have been small, its directional control had to be exceptionally high to be effective on such a potentially massive frame. How does a world of such apparent simplicity generate such precise and complex behavior? This line of reasoning leads us to a cascade of implications, each more demanding than the last. First, if the object is merely large, then the outgassing jet must be exceptionally sharp and well collimated to produce any noticeable effect. A diffuse cloud of gas would simply wash over the immense surface area, its force dissipating without a trace. But if the object is very large, then even a single focused jet may be insufficient. It would require a coordinated array of many such jets, firing in concert, a synchronized symphony of thrust to impart a net force on the entire structure. And if the object is truly colossal, then we must entertain the possibility of a mechanism entirely novel to our science, perhaps involving super-cold carbon monoxide or other volatile ices with peculiar phase change properties, substances that could store and release energy on a scale capable of bending the path of a mountain. Where does the line between a natural comet and something else begin to blur? The ultimate consequence of this analysis is that 3I Atlas presents us with an exquisite inverse problem. We observe the outcome, the subtle deviation in its orbit, and from that single data point, we are forced to work backwards, deducing the architecture of its internal vents, the geology of its icy matrix, and the very principles of its operation. It transforms the object from a mere curiosity into a complex equation written across the sky, its solution holding the key to understanding its origin and nature. What other secrets are encoded in the simple fact of its altered path? And if its physical dimensions pose a profound challenge, its chemical composition unveils a mystery of a different order. The surprising abundance of water ice detected in its coma, a quantity far exceeding what was anticipated, speaks not to its immediate activity, but to its ancient past. This high water content is a ghostly echo, a chemical signature that may have been locked within its core since its formation. It suggests that 3I Atlas could have originated in the cold, distant reaches of a stellar system, a place where water ice is the dominant building block, much like our own Kuiper belt or Oort cloud. But this then raises a deeper, more resonant question. Does this water-rich profile act as a forensic fingerprint, inadvertently revealing the nature of its parent star? Current planetary formation theories suggest that the chemical makeup of a body is a direct reflection of the protoplanetary disk from which it condensed. A composition so rich in water, and potentially similar in other elemental ratios to our own solar system, points toward a stellar nursery with a chemical abundance not unlike that of our Sunday. It is a compelling, almost intimate notion that this visitor from the interstellar dark may be a long-lost sibling, born from a star that could be a chemical twin to our own. The water vaporizing from its surface carries within its molecular bonds the story of its birth. Are we, in analyzing its spectral lines, reading the autobiography of another sun? Yet, the mainstream explanation would caution against such a hasty conclusion. The presence of water is ubiquitous throughout the galaxy. It is the third most common molecule in the universe. Its detection, therefore, is not uniquely special. Scientists suggest that many interstellar objects could be largely composed of water ice, as it is a primary condensate in cold molecular clouds. The anomaly of 3I Atlas may not be the water itself, but the specific isotopic ratios or the presence of complex organic molecules alongside it, the subtle impurities that act as a true birthplace signature. But our instruments, even as advanced as they are, may not have been able to discern these finer details during its brief passage. So, we are left with a broad, suggestive, but ultimately inconclusive clue. Does the prevalence of water throughout the cosmos make it a universal marker of habitability, or a universal solvent that erases the very distinctions we seek? The speculative hypothesis, however, pushes this idea into a more profound realm. What if this water-rich composition is not a random artifact, but a deliberate commonality? If the object's trajectory and proposed propulsion mechanism already hint at a complex internal structure, could its chemistry be part of a larger pattern? The laws of physics and chemistry are universal. The processes that led to the emergence of life on Earth are presumably replicable elsewhere, given similar conditions. A water-rich object from a sun-like stellar system could be more than a mere rock. It could be a seed, a vessel, carrying the very same prerequisites for life that exist here. This transforms it from a scientific specimen into a potential biological messenger. Is the water we see simply a natural resource? Or could it be the medium for something far more complex, frozen in time within its dark, interior chambers? This duality of interpretation is the core of the scientific pursuit. On one hand, we have the conservative Occam's razor approach. 3. Atlas is a rare but natural planetesimal, ejected from its home system, its water content a predictable outcome of cosmic chemistry. On the other, we have a hypothesis that grows increasingly expansive, an object of substantial size, guided by a precise, natural throttle system, and composed of material that mirrors the building blocks of our own living world. Each piece of data does not close a door, but opens a corridor to ever more fundamental questions about our place in the cosmos. The water vapor, glowing in the solar wind, is not just a cloud of gas, it is a question written in chemistry. Are we looking at a reflection of our own origins, or are we reading a map that points toward a destination we have yet to imagine?